So just by this simple one-way ANOVA, by now you should have some understanding about the ANOVA. Okay, you really compare the variance because you have the sum of square divided by degree of freedom. This is your variance actually. Okay, in other words, and whether or not you reject the null hypothesis, it depends on the ratio between the among group where some mean square and the within group mean square. If there's an effect of the group, the difference between group is very large, then the difference for the group mean to the overall mean should be very, very large. Okay? And if the effect on each of the group, each of the treatment is very consistent, then this within group mean square will be very, very small. Okay? So that means that the F-test actually is to test the ratio that explains variance. Okay, the variance that explained by the factor, the treatment, okay, with the variance that is not explained by the treatment. So that means that now, even though you do not do any calculation, okay, but whenever you see the plot, you see the data, you see the plot that summarizes the data, you should have some intuitive understanding of the ANOVA. If the ANOVA will perform on this data set, what would be the result look like? Okay. So this is an example. Okay. So I show you two different data sets, and these two data sets have the same mean, overall mean, and the same overall standard deviation. Okay. So in this case, this is the measurement for the body height of 100 students from the class A, 100 students from the class B, and 100 students from the class C. This is the same. Okay. So the overall mean, just like what we calculate, how we calculate just now, and the overall standard deviation is the same between these two data sets. Okay. But this is just mean and standard deviation. But the exact value is not the same, right? Okay, for each of the class. So now you can compare between these two ANOVA tables. So the ANOVA table, for first thing first, you need to calculate the sum of square. Okay, then calculate the degree of freedom. After that, calculate the mean square. Of course, the mean square in this case is depend on the sum of square. It's not depend on the degree of freedom because the degree of freedom between these two data sets is the same. But you know that the total sum of square should be the same, right? Because the total standard deviation is the same, the total variance is the same. So the only thing that can be differ between these two data sets is the sum of square between group and sum of square within group. You can see the total sum of square is very similar. Okay. But for this one, you can see the clear difference, right? Okay. Between these three group. So you expect there is a larger sum of square in the treatment. Okay. Whereas this one, you cannot see the difference between group. Okay. And you expect that there's a very small sum of square for the treatment. Okay. And you know that sum of square of the treatment is the calculation between the difference between the mean for each group minus the overall mean, right? Somewhere here. Okay? Minus the overall mean somewhere here. So this one you can see there's not much different from the overall mean. However, there's a residual. So if you use a software, some software they say this is a residual or within group or error. Okay, but that means the same things. That means that those variance that is not explained by the factor, in this case, is the different classes. Okay. So in this case, you can see the variance that is not explained by differences, different classes, is explained by some other things, but you don't know what. So the sum of square is fall into this category, the residual sum of square. Okay. So if you check the sum of square or the standard deviation, the variance for each of the data set, so you can see this is quite small, close to 0.1, and this one is much larger. This is within group variance, right? Okay. If you add this up, then this will be very large. How about this one? So these two data sets has the same overall mean, but the sum of square, overall sum of square is different. Okay. So if you calculate the overall, you can see the difference, right? Okay. This one, the total sum of square is much larger than this one, total sum of square. Okay. But you can see the within group sum of square is more or less the same. Okay, this within group sum of square. It's very similar. Okay. So the standard deviation for each group is close to 0.1. Okay. So that means that the residual is the same. See here, the residual is the same, very similar. Okay. So the main difference here that cause the total sum of square differ is because of the differences between the group. So you can see the value here. This is 0.01. This is 17. Okay. So this is the last one. So I just show you all the value. Okay. So I show you the overall mean, overall standard deviation, and also the mean for each group and standard deviation for each group. Okay. So you can see this overall standard deviation is much larger. Okay. And the standard deviation for each group also quite large. Okay. Even though, so the total sum of square is quite different between these two data sets. Okay, you can see the variation, right? It's a lot of difference. So even though in this case, the difference between group, the sum of square between group is larger than this one. Okay, but because of the unexplained error, the within group sum of square is very, very large compared to this one. Okay. So in this case, when you continue the calculation to calculate the mean square and then calculate the F value, you'll see that for this data set, they show the significant result. But for this one, they do not show the significant result because this error is very, very large. It's very, very large. Okay. So that means that when the major principle of the ANOVA is to see the ratio between the explained variance to the unexplained variance. Okay, you need to see these two things at the same time. Okay. So when you conduct the ANOVA, you have to make sure you follow the assumption, okay, your data set. So first is the normality, as usual. Then the second one is the homogeneity of variance. And the third one is the independence. Okay. In some of the textbooks, they say that the ANOVA is quite robust if you have a large sample size and your sample size more or less equal between groups. If you violate a little bit from the assumption, okay, it's still acceptable. Okay? But you have to report this in your result.